of time as seen from different places. So let's see, if you're here, the Venus as seen from Earth is crossing this part of the Sun, as seen from different part of Earth is crossing here. So you can time how long does it take, and if you solve the equations, again, you actually can measure the distance of Venus from the Earth and of Venus from the Sun, and therefore you can measure the distance of Earth from the Sun. So you will know how big astronomical, what we call astronomical unit is, namely the average distance of the Earth from the Sun. So surprisingly enough, this is a very hard thing to do, mostly because these are very rare events. Namely, you will have a transit of Venus, then there will be another one about 12 years later, I believe. Sorry, 8 years later, and then you have to wait 100 years for the next one, 100 plus. So we just had one this June, and the next one will be in 2117. Now, I'm definitely going to be wrong, but nevertheless, you know, you kind of have to do something. This is more than 100 years from now. So there's special. So when Edmund Halley proposed this idea, there wasn't going to be another transit of Venus for a while, so he didn't actually do it himself. So people knew these are coming. By then they understood the mechanics of the solar system very well, so they could predict when the next transit of Venus is coming. And there was a pair of transits of Venus in 1761 and 1769. And somewhat surprisingly, maybe now thinking about the different countries in Europe at the time, which were also competing for colonies and competing for power, they sent different expeditions to observe the transit of Venus and to actually, as part of that, to measure the size of the astronomical unit. So Captain James Cook was one of the people. Of course, they were doing other things. They were discovering new islands and probably claiming them for the crown. But also, one part of his expedition was to measure the precisely how long the transit of Venus was from somewhere else on Earth. Remember, you want to get the base of a triangle in order to measure distances precisely. I should mention this. Unfortunately, I never took French, so I can never pronounce it correctly. He went to observe the first transit somewhere in the Indian Ocean. On the way in, it turns out that what used to be a French colony no longer was French colony, so he couldn't land where he was planning to do the observations. So he did the observations from a ship, but that kind of was not very good because the ships are rocking and you couldn't do it very well. The next one is just coming 8 years later, so he decided not to even go back to France because that would take, the travel was really dangerous. It wasn't just security, you couldn't, taking shoes off, this was really bad back then. And so he decided to stick around and observe it again. He was clouded out. Well, then you're done because the next one is 100 years later. So he went back to France. It turns out he was proclaimed dead, and his wife remarried, and of course he didn't have any possessions anymore. So the astronomer was really a tough job back in the 18th century. Now we travel in style. Anyway, at the time, all these measurements were used to measure the size of the astronomical unit, which is again the mean distance of Earth from the Sun, to using modern units 153 million kilometers. The best modern value is very close, so this was just a little bit off, and we know that value to precision of about 30 meters. And that's because we send space probes out there in the solar system with atomic clocks on them, and we can tell them, send me a signal exactly at that time, and then we can time the arrival of the signal to Earth, also using atomic clocks, and just by measuring, dividing by timing this, and we know the speed of light very well, we actually know the size of the solar system with extreme precision. But this is 21st century now. And so we know with precision 30 meters out of 150 million kilometers. So how long is 1 AU? I drove yesterday from Columbus, Ohio. Not really in straight line, but pretty close. So it's roughly 300 kilometers. I took slightly more than 3 hours, but let's say you drive about 100 kilometers per hour. If I wanted to drive from here to the Sun, it would take me 150 years. And I would have burned about $10 million worth of gas. So 1 AU, and that's just 1 AU. We started talking about really large distances in the universe here. And this is just the distance of Earth from the Sun, which is not the farthest away planet in the solar system. Jupiter, for example, is about 5 AU away from the Sun. So now I want to use that base. Now I have the base, which is the distance of the Earth from the Sun, and I want to use this as a base of my triangle. I want to measure positions of the stars using the fact that Earth moves around the Sun. So if I look at some faraway star in June, and then I wait 6 months later, the position of some nearby star with respect to the farther away stars will be changing. And so just a reminder, because we'll be talking about really small units of angles, the whole circle is divided into 360 degrees. 1 degree we divide farther into 60 arc minutes, and 1 arc minute is divided in 60 arc seconds. And in astronomy now we'll be dealing with angles. It's kind of, for example, the angle we call parallax, we'll introduce in a second, which are always smaller than 1 arc second. And that's because stars are really, really far away from, other than the sun, they're very far away in the universe. Just roughly angular size of the moon on the sky and the sun, about half a degree. Okay, so here's the idea. This idea is an old idea. Already when Copernicus, Polish astronomer from 16th century, who proposed that the Earth really moved around the sun, when he proposed that, one of the scientific oppositions to his idea was that we should actually see what we call parallax. When we look at some star in June and then we wait 6 months, that star should move on the sky because the position of the Earth has changed. And the fact that we haven't seen those such parallaxes was actually used against Copernican idea. This was a valid scientific objection, but it turns out we couldn't see it because these angles are so small that we now had to wait until 19th century in order to measure them. So as I mentioned, these parallax angles, this is the parallax angle here, are tiny. They're always, even for the nearest star, they're less than 1 arc second. So here's just a little animation. Here are we in June, there's some foreground star, we measure its position in the sky. These are vastly exaggerated angles. And then I wait until December, the position of the star is a little bit closer. So people tried to do this measurement ever since Copernicus has proposed his idea a little bit later. You need telescopes, but really they had to wait until 19th century before the precision of measurements became so good that they could actually do it. So we went and measured the size of the Earth about 2,500 years ago. We knew the size of the solar system with ever-increasing precision already in 17th century and 18th century. Now in 19th century, we can use that to measure the distances to stars. This is huge. Now we are getting some idea about there are these objects on the sky. They're just sources, point sources. We can resolve them. Suddenly we are able to measure distances to them. And so, as often happens in astronomy and other fields, what happens is that technology grows, people are able to do something, and more than one person really will do the measurement, but as always there is a winner. Somebody in this case was Wilhelm Struve from Germany. He is the person most credited with the best measurement. He measured the distance to a star called 61 Cygni. This is the 61st brightest star in the constellation of Swan, and the parallax is only about 0.3 arc seconds. Translating this to astronomical units, this is about 600,000 astronomical units. So distance from the Earth to the Sun is 1 astronomical unit. Now if I wanted to drive to that star, I don't even want to do the calculation. It's ridiculous. The nearest star, even the nearest star, is more than 3 light years away. The light has to travel several light years. So universe, it's mostly empty, and it turns out we live in the crowded neighborhood because we live in the galaxy. So parallaxes are still being measured. There was a beautiful satellite in early 90s called Hipparchus, named after a Greek astronomer. People used to measure parallaxes on individual stars, and you have to not just wait 6 months, but if you really want to get good measurement, you do the parallax measurement over several years, because this allows you to get a better measurement. And if you have to do it for a handful of stars, and you have to do it over many years, it gets tiresome very quickly. So people had the idea that if we had a satellite, we send it above, obviously as satellites go, we send it above the atmosphere, we'll be able to observe the whole sky, and because there is no atmosphere, there is no what we call seeing, we'll be able to measure positions of stars very well. And so the Hipparchus satellite has measured positions of about 100,000 stars, parallaxes and distances, to precision of a few percent. About 300 light years is about what we call 100 parsecs. There's this unit of distance in astronomy called 100 parsec. So now we have distances to about 100,000 stars, but they're all very close. Turns out 100 parsecs or 300 light years, it really is just the solar neighborhood. Turns out the galaxy, the bigger object that we live in, it's much, much bigger. So now we want to also be able to measure that distance. There is a mission underway called Gaia, which is again a European mission, which is going to, I think, is being launched next year. In astronomy, we're slightly superstitious, namely the launching of payloads is quite dangerous, namely that they can actually, you know, fall. And so until something is launched, you know, we don't really, but you know, we're hoping this will work well. So Gaia will be able to measure parallaxes basically throughout our galaxy. But this is skipping ahead. But of course, we actually know pretty well already how big the galaxy is, and this is where this is becoming a little bit more complicated. We cannot do geometry anymore. All this beautiful thing about measuring angles, having the base, just doesn't work anymore because my ability to measure angles is just limited, and even using satellites, I can only measure angles which are that small. There's a universe is even bigger. So now, if I want to measure distances to things which are even farther away, I have to come up with a different method. So the method generally is called the standard candle. If there is some object in the universe, a star of some kind, that for whatever reason has the same what we call luminosity, namely how much energy you produce per unit time. For example, watt is a unit luminosity, 100 watts. This is 100 joules per second. And if I have this standard candle or standard light bulb, and I observe it at different distances, the farther away it is, the fainter it's going to be. If I look at the bright light from nearby, it's going to be very bright, it will have what we call large flux, what we call F. As I increase the distance here,